All right, this is the last chapter we're going to study in this course, and we'll pick it up. This is chapter 9. We'll pick it up with the second semester in chapter 10. Anything we need to deal with? Okay.
Question real quick.
Yes.
For the second part of this chemistry. When do you want to get the schedules?
When do what?
When do you get the schedules out, or how many labs is there in that 10 weeks?
Let me see. Not as many as in the first semester. I've got 5. So it's like every other week we'll have a lab. Or 2 of them might come together. It depends. Well, I try to match the labs up with the material we're covering. So they may come in rapid succession at times. Then it'll slack off toward the end like it is now. And then you can focus on closing out this course and spending time on other courses that may be giving you more trouble. I can't imagine one that gives you more trouble than chemistry. Okay, chapter 9. In chapter 9, we're going to continue discussion of bonding. And like I said at the beginning of chapter 8, we're taking these in basically chronological order and in the development of concepts about orbitals. And we're going to get into more useful theories and techniques in this chapter. Okay, we're going to start off with a problem. We know that the Lewis structure for methane should be 4 electrons here, 4 electrons there, which equals 8 electrons, which means we have a carbon in the middle, like that, like that, like that, like that. Okay, so, and that's 2, 4, 6, 8. So all of them are used up. And 4 groups around the central atom means tetrahedral. And since there are no lone pairs, the electronic structure and the molecular structure are the same. So we should think of methane as carbon in the middle, and then we've got the hydrogen here. We've got a hydrogen here, and we got one in the back. Actually, that's not the right place for it. Let's try that again. Let's do the triangle first. Now we got a carbon in the middle and another hydrogen up here. So that gives us a tetrahedral arrangement. And all the bonds, this is theoretical and experimental. All the bonds have been confirmed to be exactly the same strength, exactly the same length. Right? But we also know that from the valence bond theory and the localized electron model that follows from it, that when you get a bond forms between this atom and that atom by simply overlapping atomic orbitals. So if we look at the electronic structure for carbon, we have 1s2, 2s2, and 2p2. And the valence electrons are here. So we're only concerned with these. Well, we know that s orbitals are spherical, right? And so you got the nucleus in the middle, and you got this s orbital out here. But p orbitals are dumbbell shaped. So they're gonna be like this, and then you're gonna have like that, and then into the board and out of the board. And so you have two different types of orbitals from carbon that are gonna have to overlap with a single type of orbital, right? The 1s orbital from hydrogen. When they do that, can we expect to have identical, equally spaced and equal strength orbitals if we overlap this one with two hydrogens and overlap these with the other two hydrogens? This model at this point is telling us that those bonds are not equal. You can't get equal spacing with this overlap and that overlap. You can't get the perfect tetrahedron, but we know that the tetrahedron is the way it is. Experimental data tells us that's it. Okay, this is one of those cases where you say, all right, if the theory doesn't work, what do you do with it? All right, remember the three possibilities? You modify it, which is what we're going to do with this one. You tweak it, or you restrict its use, which we don't have to do here because we're going to tweak it. And the third one is throw it out and start over. We're not going to do that either. Okay, so what's the tweak? The tweak to get this one to work right is called hybridization. Here's how it works. Well, let's see. Let me finish this slide. Right, shape of the orbital, there we go, tetrahedral. Bond angles are all 109.5. Okay, we know that's predicted and experimentally confirmed. There are the valence orbitals for carbon. And if we do overlaps, we're not going to get those equally spaced bonds with the hydrogens. Okay, so here's the fix. I think this was proposed by Linus Pauling. What happens is before the bonds are formed, you do have the two electrons in the s orbitals and two electrons in the p orbitals. But when the bond forms, those s and p electrons, like 2s and 2p electrons, they hybridize and they form what's called an sp3 hybrid orbital. And then these are all equivalent. How many of them do we have? Well, we need 4 of them, right? We need 4 sp3 orbitals to overlap with 4 hydrogens. 1s orbitals for the hydrogens. These are from the hydrogens, these are from the carbon. So those hybrid orbitals, and each orbital is designated as an sp3. So if you look at it this way, let's see, you have 2s right here, and you have 2 p's, right? You have 3 possibilities there, and those guys come together. And whenever you hybridize orbitals, you got to end up with the exact same number you started with. Right? So with our hybrid orbitals that we call sp3, you started off with 4 of them, you end up with 4 equivalents there. Okay? That's the fix, hybridization. And when you do that, I was right, Linus Pauling did it in 1931. Excuse me. And you can tell what to name the hybrid orbital based upon how many of these that you use. We're using 3 p's, so that's why the p3 here. And we're using 1s, so that's s. And that also tells you that with 3 of these and 1 of those, you need 4 total. And they're all equivalent, pointing to the apexes, the corners of the tetrahedron. Okay. Now, we could also set up something over here. Let's see, if we have, let's say we have hybridization. Hybridization over here. And the geometry here. If you have the need for an sp3, this is always going to be tetrahedral. Okay. We'll set that up. We'll leave that one there because we're going to add to it. Now, the other thing we also know is when we combine these orbitals, the s orbital is at a lower energy than the p's. All right, so the hybridized orbital is somewhere in between. I didn't draw it correctly here. If I had drawn it on an energy diagram, then the two s's would have been here, and the three p's would have been, excuse me, and the p's would have been here, and then the hybridized orbitals, the sp3s, would have been in the middle somewhere, right there. But they would have, let's see, how many you have? 1, 2, 3, 4. So 25%, 75% character for the p orbitals. That means their energy should be like 75% from here. 1, 2, 3. It should be a little higher, right about there. If we're looking for the derived energy for this hybridized orbital, it should be close to that. And that's what they look like. Right? The one on the left is the atomic orbitals, and then the hybridized orbitals are on the right, pointing toward the corners of the tetrahedron. And that's an artist's rendition of what you should expect to see if you got down small enough and you could see the electron clouds and so forth and so on. All right. So can we use this also for the ammonia molecule? Right? Remember, the ammonia molecule is, electronically speaking, the ammonia molecule is tetrahedral. We say like that, then this is 5, this is 3, that's 8. So we should have like this, there, that's 6. So we have 2 more right here. So the electronic structure for ammonia is going to have this hydrogen in the back, and then hydrogen here and hydrogen here along there. So the electronic structure is tetrahedral, right? But the molecular structure, of course, is a triangular pyramid. But as far as the bonding goes, we're going to use the sp3 model. We're going to take the nitrogens, 2s and 2, it would have a 2s2 and a 2p1. And of course, a 1s2 that's not being used. So that's 2, 4, 5. And that's not right. Sorry, that's not right. This should be 3. Sorry. There you go. So if we hybridize these, then you've got 1s and you got 3 p's. So you can have an sp3 orbital, right? We're going to have 4 of those. 1, 2, 3, 4 of those. And we're going to put 2, 4, 6, 8 in it. 1, let's see. Hans rule. 2, 3, 4, 5, 6, 7, 8. So these will be the bonding orbitals, and this will be non-bonding. And that's where these go right here. Those two, that lone pair. Okay. All right, so that's what we did. We used the Lewis structure. VSEPR told us what the geometry is. All right, we use an sp3 hybridization. And we get a similar structure to methane, only now instead of an atom up here, we have a lone pair occupying that orbital. All right, let's try another one. How about ethylene? Remember, when you're using these theories, we start from a real compound. This exists, C2H4. It's called ethylene. So if we take 2 times 4 is 8 for that one, and 4 is this one. So we have 12 electrons. Now we're going to have a carbon attached to a carbon. That's the way we write organic molecules. That carbon is attached to the other carbon, and then the hydrogens get placed. And so we have like that. Okay, have we used up 2, 4, 6, 8, 10? We've used up 10 of these. Right? Yeah, everybody's accounted for. So we have 2 electrons that have to be placed somewhere. So we put them here. Can't put them on the hydrogens. They've already been used. And then we try to make an octet, remember? We'll make an octet. We're going to move these 2 over here into a double bond. And that gives us 2, 4, 6, 8, 10, 12. So we're good. Now, what's the structure? Well, we don't have any more lone pairs. So this is 1, 2, 3 groups. So 3 groups is trigonal planar, right? Trigonal planar. In fact, it's trigonal planar around either one. All right, 3 groups around that one, 3 groups around this one. Both of them have trigonal planar. Okay, so how do we get trigonal planar? Well, in that case, we only need to overlap 1 s and 2 p's. That gives us 3 hybrid orbitals. 1 here, 1 here, 1 here. Now this hybrid orbital only accounts for that one, that one, that one. Okay? This one, we have an sp2 hybrid. Actually, 3 of these. 3 sp2 hybrid orbitals. And then we have 1 leftover unused p orbital. Right, so for carbon, that'd be an unused p orbital for this carbon, unused p orbital for that carbon. What happens to those p orbitals? Those p orbitals overlap for the double bond. And so you get these unused p orbitals here and here, and they form that double bond. Okay. So if we have a trigonal planar situation here, trigonal planar structure, that's an sp2 hybrid. Yeah, I think there's more in this slide that tells us. Yeah, trigonal planar around each carbon, and the bond angles are 120 degrees. There you go. So instead of sp3 hybrid, which would give you the wrong geometry, we go to sp2 hybrid, which will give us the trigonal planar. Because we only need 3 identical orbitals. All right. Now we're going to introduce another idea. What do we call, I get the feeling we've mentioned this before. I'm going to tell you again. So when you have a single bond on axis between 2 atoms, that bond is a sigma. We use a little Greek. This is sigma. And when you form the double bond, you can't have any more on axis bonding. right? There's only room for one. So we got one sigma here, we got a sigma there, we got a sigma there, right? All these are sigmas. And this one we call a pi bond. Just like pi r squared. That's a pi. A pi bond is always formed by off-axis overlap of p orbitals. Well, sometimes d's. For our purposes, we're going to keep it simple. Just the p orbitals overlap. And that gives you the double bond. Now, because the overlap is not on axis like this, a perfect overlap, the pi bonds are weaker than sigma bonds. But you never have a pi bond by itself. You always have a sigma first, and then the pi comes along afterwards. And you can have up to 2 pi bonds. So that means you can have either a single bond, sigma bond, or if we add a pi bond, that gives you a double. If you add another pi bond, that gives you a triple. Now, the energy, the single bond has a certain energy that's required to break it. But if you have a double bond, you have a pi in there, the pi itself is weaker than the sigma, but it adds strength to the total. So it's not twice as strong, but it is stronger if you combine the sigma and the pi. Okay. Now, talking about the energy, when we overlap an s and a p orbital, 2 p orbitals, right? We have the 2s here, and we have the 2 p's here. 1, 2, 3. Now you're only going to use 2 of these. That means we're a third of the way below. So the hybrid orbital would be right in here. 1, 2, 3. This would be the sp2 hybrid orbitals. And then you'd still have one unused p orbital over here. So that gives you 4 orbitals here that you started with 4 and you end up with 4. 3 of them are hybrids and 1 of them is unused p. At those energy levels. This energy level is going to be like 2/3 of the way. Wait a minute. I'll circle the wrong. There. 1, 2, 3, 1, 2, 3, and then this one is the same as it was over here. So the energy character of these hybrids will be actually closer to the S than the sp3s because you have fewer p orbitals and, as compared to the s orbitals. That's what they're trying to get at with this energy diagram. There we go. So this is what it would look like. An sp2 hybrid gives you a trigonal planar. Right? They're all pointing 120-degree angles from each other. And then you have that unused p orbital sitting up here. And that's the one that overlaps with its neighbor to give you the pi bond. All right. And this is calculated from the mathematically calculated from the theory. This is what the electron cloud would look like. These are probability distributions, remember. These are not actual places where the electrons reside. They're just the most probable locations for the electrons. Okay. So we've identified sp3 hybridization, sp2 hybridization. This is what the ethylene molecule would look like, where you get the overlap here. And we're still talking about the localized electron model. Right? We still are saying that these electrons belong to their parent atoms, and they're only shared in an overlapping fashion. And the reason I'm emphasizing that is because the next step is where you just throw that all out all together. And you create new orbitals that belong to the whole molecule. That's where we're headed. Okay, how about carbon dioxide? Let's see, we have CO2, that means 4 here, 12 there, 16 electrons we have to deal with. So we have a carbon in the middle, we have an oxygen and an oxygen. That's 4, right? 12 electrons we have to place. 2, 4, 6, 8, 10, 12. There we go. Used them all up. Now we got to form our octets. So we know from formal charge distribution that the best way to make an octet is to move 2 from this side and 2 from this side. Okay. So that would be our Lewis structure, our best Lewis structure for carbon dioxide. Now, how are we going to hybridize this carbon? Right? What about this molecule? It's got 2 groups, right? It's linear, correct? So now we got a linear situation. So how are we going to hybridize carbon to give you linear? How many hybrid bonds do we need? We only need 2. Right? We only need 2 for the sigmas. So that means we just need 1 S and 1 P to hybridize. And that gives us, right? If we get 1 S and 1 P from the other side, that gives us 2 hybrid orbitals. So that hybrid orbital gives us 180 degrees. Let's see, this is 109.5. This is 120 degrees, and this one is 180 degree bond angle. All right, so this is going to be represented by an SP linear. So if we draw the energy diagram for this, we've got the 2 S's from carbon, and we've got the 2 P's here. We've got this one, 1, 2, 3. We're only going to use one of those and one of these. So that means the hybrid, the SP hybrid is going to be right here. There's 2 of them, right? One from here makes those. And these unused p orbitals stay at the same energy. Okay? So that means that the carbon, as far as carbon is concerned, it's got an sp hybrid this way and this sp hybrid that way. What does it overlap with? It overlaps with hybrid orbitals from oxygen, right? But oxygen has what? It has 1, 2, 3 around it. So oxygen would have to be an sp2 hybrid to give you 3 equivalents around here. sp2. So around the oxygen, you're going to have an electronic structure of trigonal planar. And around the carbon, you have a linear. Okay, so the shape around the carbon is linear, and the bond angles are 180 degrees. There we go. And the next slide, I think, okay, we've combined an S and a P to give us sp hybrid. That leaves 2 p orbitals at the same energy level they were, and they're available to do what? They're available to do pi bonding. So remember, if this is sp2, how many p orbitals does it have left over that it can use? This one has 1 p over here. This one has 2 p's, so it can have a p like this and a p like that. And this one has like that, like that. So this one's going to form a pi bond like this, and this one's going to form a pi bond like that. That's kind of messy. I think we got a picture here that works a little better. There we go. So you see that the oxygen is trigonal planar in its electronic structure, right? And it's got 2 lone pairs that are occupying 2 of these sp2s. And one of them is used for a sigma bond. But then you still got those unused p orbitals. So what we do is actually rotate this oxygen that way, and this one stays. So that gives us unused p orbitals this way here and this way here. Right? So they don't get in each other's way when they start to overlap with the 2 p orbitals from carbon. That's what we're trying to show in this picture. Might work better if we had models to play with, right? Like play with models. I'll try to get some together for second semester. Who's coming back? You're coming back. You're coming back. You had enough. You had enough. Okay. All right. Because the first thing we're going to do in chapter 10 and 11 is look at actually geometries. And they're not like the geometries of that we've studied here with this type of geometry. We're talking about geometries of extensive geometries of, say, stacking metal atoms and stacking ions and that type of thing. So we just go from sublime to ridiculous. But if there's one consolation, this 3D visual 3D stuff, women tend to do better than men with that. Yeah, that's been my experience anyway. It's taken me a long time to develop any competence with this geometry stuff. And I went through, inorganic, organic series and all that stuff, and I just barely squeaked by. Okay. So here we have the sigma orbitals are forming between the sp hybrid on carbon and the sp2 hybrid on oxygen, and that's leaving out the unused p orbitals. Then I think we're going to add. Are we going to add the p orbitals? No, they were in the previous slide. These slides are backwards. I should have put that one first. Okay, how about dinitrogen? How can we treat it? Does it need to be treated with hybrid orbitals? Well, let's see. So if we have dinitrogen, that means 5 and 5 is 10 electrons. Okay, so we have nitrogen here, nitrogen there. That's only 2. So we have 8 electrons. 2, 4, 6, 8. 2, 4, 6, 8, 10. 10 electrons, right? Yeah. Okay, so we've got to make an octet. We're going to move those 2 over here, these 2 over here, and I'm going to move those lone pairs on this side. That's usually the way you'll see it. So that's our Lewis structure. Right? How do we do that? Well, if we look at each individual nitrogen, we've got 1 on this side and 1 on that side. So that's 2. That's linear. So we still have an sp hybridization for nitrogen and sp hybridization for that nitrogen to overlap and give us this sigma bond right here. And you've got an sp going this way and an sp going this way, right? For those lone pairs and for this overlap. Right. So what do you got left over? Well, you've got unused p, unused p, unused p, unused p, perpendicular. Right, so we get overlap here, we get an overlap there, and here, and here. So that's why you have 2 pi's. In this case, both pi's are between these nitrogens. In our previous example, carbon dioxide, you had a pi on one side and a pi on the other. But it's a similar concept, the way it works. Right? You've still got sp hybridization for a linear molecule. And then we have the unused p's that we use to form the pi bonds. So we have a triple bond here instead of a pi on one side and a pi on the other side, we have 2 pi's between them. Right? And that's what it looks like. Okay. So now let's try a different molecule and see if this hybridization can be extended even further. This is getting in the way. Let me just move that out. How about PCl5? We've done that one before. Okay. So we have 5 times 7 right here, plus phosphorus, which is 5. Well, it's 40. Right, 40 electrons. Okay. So what do we have with 40 electrons? Well, we have phosphorus in the middle. We have 5 chlorines around it. So that's 2, 4, 6, 8, 10. We have 30 electrons that have to be placed. 2, 4, 6. We place 6 around 5 chlorines, we get rid of all of them. Okay, we used up all our electrons. What is our structure? We have 1, 2, 3, 4, 5 groups, which is trigonal bipyramid. Right? Trigonal bipyramid. And just, well, let's do it like this. Let's form our trigonal base, and then we got something up here and something down here, and phosphorus in the middle. So we got a chlorine there, chlorine there, chlorine there, chlorine there. Right. So our bond angles can either be what, 180? We can have here to here, which is right angle. We can have here to here, which is 120. So we can have 90 degrees, we can have 120, we can have 180 degrees. Those are all possibilities for a trigonal bipyramid. So we have 90, 120, 180. How do we get that? Well, phosphorus, we can go up to sp3, right? Use all the S's and all the P's available to phosphorus, right? Because it's underneath nitrogen. That means it has available the 3S and 3 P's, right? It's in the next, it's down one. That only gives us 4 orbitals, and that's tetrahedral. We don't need tetrahedral. We need trigonal bipyramid. So what do we do now? We pick up a d orbital. Can we do that though? What about phosphorus? Right, phosphorus has 15. Right, 15 total. So that'd be 1s2, 2s2, 2p6, 3s2, 3p. Let's see, this is a 10, 12, 3p3. Well, no, you remember if you have a principal quantum number of 3, if n equals 3, what can L be? L can be 0, 1, or 2, S, P, or D. So phosphorus does have access to d orbitals. So we're going to take an empty d orbital and hybridize it with our SPs. Okay, so this is going to use a D, an S, and a P. All right, so there's the shape, is trigonal bipyramid, and bond angles are 90, 120, 180. And we're going to get a DSP3 hybridization. We don't have to hybridize chlorine because chlorine has 1 sigma bonds sharing, and one of the 5, right, we get 5 DSP3 hybrids. Right? We got 3, 4, 5. That means there are 5 of them. And chlorine just overlaps one of its p orbitals. Yeah, overlaps one of its p orbitals with each one of these DSP3s. So chlorine doesn't have to hybridize. Okay, that's as far as we're going to go with that one. Now we're going to look at xenon tetrafluoride. Xenon. Okay. Yep. Okay. What's the electronic shape of this one? Well, we got 8 there. We got 4 times 7 is 28 there, which is 36. Okay. Xenon in the middle. We got 4 fluorines. 2, 4, 6, 8, which would be 28. 2, 4, 6, 8, 10, 12, 15, 16, 18, 20, 22, 24. So we got 4 electrons left. 2, 4. Okay. How many do we have around the xenon? 1, 2, 3, 4, 5, 6. We got 6 groups. Let's see. I left out groups. This has 4 groups. This has 3 groups. This has 2 groups. This one has 5 groups. And this one, octahedral, has 6 groups around the central atom. So how are we going to hybridize that one? Well, notice where xenon's located. It's way down in the 5th period. It definitely has access to Ds. So we need 5. We just take 2 Ds. That needs to be 3. 2 Ds, better than that. 3 Ps and 1 S. That gives you 6 hybridized orbitals. And what are the bond angles? Well, where do these lone pairs go? It's going to be like that. Right? So the fluorines are going to be on the square, and the lone pair is going to be down here and down here. And xenon's in the middle. So the bond angles are 90 degrees. I guess you could technically say the bond angle from here to here would be 180, but the nearest neighbor is 90 degrees. Octahedral, 90 degrees. Okay. D2sp3 hybridization gets us there. We also know from experimental data that this is where all the atoms are located. And one piece of evidence that tells us that is this molecule is nonpolar. That's the only way you can get nonpolar out of this arrangement. All right. There's the hybridization. Fluorine doesn't have to be hybridized because it's only got 1 sigma orbital here, 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 here. It just overlaps one of its p orbitals with the hybrid orbitals. Okay. All right, so there it is all in one chart. It's kind of out of order. All right, the chart has this one first, second, third, fourth, and fifth. But they're all up there. And that's the hybridization that's required to get us to reality. Remember, I've said it before, nature just does what it does. It's our job to figure out how to explain it. And this is one of the ways we do that. Okay. So let's see if we can do something with this hydrogen cyanide molecule. Right, we've drawn the Lewis dot structure for this thing before. We'll do it from scratch now. There's 1, 4, and 5, right? So that's 10 electrons. Carbon in the middle, nitrogen, hydrogen. So that's 2, 4, 6 electrons. 2, 4, 6. We got to make an octet over here. We can't do it from this side. So we're going to take those 2 and make a pi bond, those 2 and make another pi bond. That's 2, 4, 6, 8, 2, 4, 6, 8. That's good. That's a Lewis structure. Now, what's the hybridization around carbon? Well, it's linear, right? So that means sp. How about nitrogen? Well, it's got 2 around in it too, so it's also sp hybridized. Okay. So when you do that, how many unused p orbitals are left over? You got 2 p's here, and you got 2 p's there. So you can overlap one from here and one from here and make that pi bond. One from here and one from here and make that pi bond. Okay. Oops. There we go. Now there's a sigma bond between hydrogen and carbon. There's another between carbon and nitrogen. And then there are two pi bonds. One there, one there. Okay. We don't have time. Right. All right, let's take these examples. Let's see, we've done ammonia, we've done carbon dioxide, and we've done xenon. Well, okay, so that's a new one. So we've done ammonia and carbon dioxide already. And what are they asking for? Bond angles and hybridizations. This hybridization is going to be sp3 to give us tetrahedral. And the bond angles are 109.5 degrees. Actually, they're a little less than that. Remember why? Because that lone pair. Right? It balloons and pushes down on the other bonds. But nominally, it's 109.5 in a tetrahedron. How about this one? Well, around the carbon, right? Around the carbon, you've only got two groups. Right? So it has to be linear with an sp hybridization. That means 180 degrees. Now, what else does it want? That's it. Okay, how about SO2? Well, let's see. Sulfur and oxygen are in the same group, so they have the same number of valence electrons. That's 3 times 6 is 18. 18 electrons. So we have like that, like that, like that. That's -4, which is 14, 2, 4, 6, 8, 10, 12. We need two more up there. That. So, central atom. Okay, so we're only concerned with the central atom. The central atom has 1, 2, 3 groups, which means sp2 hybridization, right? It needs 3 places. 1, 2, 3. This is trigonal planar. And with 120 degree bond angle. Okay. Who's next? ICL5. 5. Okay, so we got 6 halogens means 35 electrons. Okay, 5 times 7. So we got iodine in the middle. We got 1, 2, 3, 4, 5. Chlorines. Chlorine. 2, 4, 6, 8. 1, 2, 4, 6, 8, 10. 25. 2, 4, 6. 6 times 5. Is that right? My count's not coming up right. 5 times 6. 35. Yeah. 5 in the middle. 1, 2, 3, 4, 5. 2, 4, 6, 8, 10. That's 25. 2, 4, 6, 8, 10, 12. 6, 2, 4, 6, 8. Something does not compute. 6 times 7 is 35. That's right. We put these in here. 2, 4, 6, 8, 10. 10 from 35 is 25. What am I doing wrong? 2, 4, 6. That's 5, 30. Oh. 6 times 7 is 42. So minus 10 is 32. And then we've got 30 around here, right? 6 times 5 is 30. There we go. Now we have 2 that have to go right here. So this has got 6 groups around iodine. which means octahedral, correct? So octahedral has possible, let's see, 90. Well, 90 is the most common. We could argue 180, but if we use all those up in the octahedral setting, we have D2sp3. Right? We need 6 groups, 3, 4, 5, 6. And KRF2. Let's see, I think these are coming in. I animated these in. Yeah, there we go. Those two. I think we're going left to right, so I better do this one first. Krypton difluoride. This one's 8. 2 times 7 is 14. So 22 total. All right. Krypton. We have a fluorine here and a fluorine there. And that gives us -4, which is 18. 2, 4, 6, 8, 10, 12. Well, got 6 left over. 2, 4, 6. So we have 1, 2, 3, 4, 5. And 5 groups, which means DSP3, which is a trigonal bipyramid. With, let's see, this one, where are these? In a trigonal bipyramid, where do the lone pairs go? Remember? They go on the triangle. They go on the base of the triangle. So we got 3 of them. All those positions around the triangle are occupied. These fluorines are at the apex. So this is a linear molecule, actually. 180 degrees. But it still requires a DSP3 hybridization for all these electrons around the krypton. Okay? And we know that's true because the molecule is nonpolar. All right, we already did CO2 and we already did ICL5. All right. So this is just a summary of what you do to use the model with hybridization. Still have to go back and draw the Lewis structure, then do the VSEPR arrangement to find out what its geometry is. And then you find out how many hybrid orbitals are required to give you that regular structure. And then you use this arrangement. Once you know this, this follows from that. All right, here are the things that are wrong with a localized electron model that actually required us to introduce that fix. The model incorrectly assumes that the electrons are localized. In other words, they assumes that the electrons belong to each of the atoms and they're only shared to form the bonds. In some cases, we have to add resonance. We've already done that, right? If you have 2 or more valid Lewis dot structures, and each one has the same arrangement of formal charges, the lowest values of formal charge you can get. If you got 2 or more of those, then you got to resonate them. Right? You got to keep all of them and just resonate them to explain using this model, explain the geometry of the molecules. Free radicals are a problem. I think we ran into one of those in the last chapter where you had just one electron. We had to treat it as a group, right? Even though the pairs or bonds were the ideal situation for the localized electron model when we're using VSEPR. But when you end up with an unpaired electron, you're forced to use it. when that's probably not the best option. Those free radicals, unpaired electrons, give us trouble. Okay, here's the most serious problem with the localized electron model. It does not give us direct information about bond energies. We can suppose, even using hybridization, that the bond energies are somewhere on that scale, but we cannot calculate the exact values for bond energies based upon this model. All right, if this is one of my short classes, then this is where I'd pause and we'd pick it up later. But since we've got lab time, I'm going to go ahead and finish it. And then we can come back Thursday and start the review. Right. And that way we don't have to rush through the review. We can get halfway through the review and then finish it the next Tuesday. And if we do that, then we'll still be on schedule for Thursday exam. And that'll give us the following week, both Tuesday and Thursday, to review for the final. We have lots of time. Okay. That's why the break was there. Because the next possibility, and this is all, let's see, this is the localized electron model, VSEPR, with hybridization. Do better than that. Okay. The quantum mechanical model was kept in its essentials and modified to go to this next step, molecular orbital model. We use quantum mechanics to give us the N, the L, the M sub L, and the M sub S principal quantum numbers to describe individual atoms. And then we tried to overlap those in this model here. That didn't work too well. Well, it works to a certain extent, right? It does jive with reality up to a certain point, except for that really one important point. Doesn't tell us anything about bond energies. So there was a lot of work done by a lot of people on the next possible model, the molecular orbital model. There's a fundamental departure. Now, with this model and that model, the localized electron model, says that the electrons belong to each atom and they only share them to make bonds. Whereas the molecular orbital model, when the molecule forms, every electron in every atom goes into the mix. Not just the valence electrons, every electron goes into the mix and they come out with a new set of orbitals, the molecular orbitals. Okay, so now the molecule is like it's like communism, right? They all share their electrons. And for all I know, the molecular orbital model was proposed by a communist. Anyway, remember we started off with Niels Bohr's planetary model, where you just had the electrons going like this. Then we went to quantum mechanics, which used probabilities to describe where the electrons were most likely to be. And then we try to use that model to form bonds. Now we're at the point where we need something better. The fundamental difference between the two is that the localized electron model still hangs on to atomic orbitals, whereas the molecular orbital model throws that out the window and creates a whole new set of molecular orbitals. And we're going to practice some of those. I mean, it can really get ridiculous. I mean, it's beyond my scope actually for some molecules. We're going to keep it really simple. We're just going to have two atoms, right? Sometimes we're going to start off with the same atoms, like dioxygen or dinitrogen. And then we introduce maybe some heteroatomic molecules with, say, nitrogen and oxygen. But that's as far as I can take it. That's as far as you need to go, actually. All right, so they both use quantum mechanics, right? The formulas that go into the quantum mechanical model are modified to accommodate molecular orbitals. So that's one thing that they have in common. Localized electrons on individual atoms versus electrons now are delocalized over the entire model. That's a word that you ought to chisel in stone in your brain. Delocalized electrons. Delocalization is lower energy and more stable. Anytime you can delocalize electron density in a molecule, you add stability. And that's what the molecular orbital model does. It delocalizes all the electrons in the entire molecule into this new set of molecular orbitals. Now, even though we create these new molecular orbitals, we still have only 2 electrons per orbital. So that rule still holds. And you fill them the same way, right? Using Hund's rule, right? If they're degenerate, remember what degenerate means. They're at the same energy level, and you have several of them, several orbitals, then you put 1 electron in each one before you can pair them up. That works for both models. Their energies are still quantized. In other words, you're either here, or you're here, or you're here, or you're here. Nothing in between. All right. So when we get atoms coming together to form molecules, they bring with them their atomic orbitals. And the number of atomic orbitals of each atom goes into the mix. And you come out with a set of molecular orbitals of the same number, the same amount, the same number of molecular orbitals as all the atomic orbitals that went in. So you conserve the number of orbitals. Now, in order to do that, we had to invent this new idea. This is mathematical, actually. But this idea helps us understand this idea is on the pathway to quantifying bond energies, right? When those orbitals go in, you create bonding orbitals and anti-bonding orbitals. So when you put, let's say, for example, if you're on this energy scale and you've got from this atom over here and this atom over here, you got these 2 atomic orbitals. When you put them together, you have to have 2. You have to have 2 molecular orbitals, right? So we're going to have 1 at this energy level and 1 at that energy level. So you have 2 going in, 2 coming out. Right? We usually put tie lines to show where they came from. So now this molecular orbital, this is the bonding orbital. And this is the anti-bonding orbital. And it's named anti-bonding because it's higher energy than the atomic orbitals were. So it doesn't add anything to the whole scheme. It doesn't make the molecule more stable. It makes it less stable. The electrons that are in the anti-bonding orbital make it less stable, and the ones in the bonding orbital make it more stable. So where we're headed is, if you have more electrons in the bonding orbitals than you do in the anti-bonding orbitals, then you have an overall stability outcome. Okay, I think I've got 2 or 3 videos coming up that'll help describe. And we still keep the terminology for sigma and pi orbitals. Right? The molecular orbitals that are named sigma are between atoms, and those that are off axis are still pi's. This statement emphasizes the fact that once the molecule forms, forget about the atomic orbitals. They don't exist anymore. Right? When you have a molecular orbital system, atomic orbitals are gone. They're replaced by molecular orbitals. The only way you can get the atomic orbitals back is to break the bonds, separate the atoms, and they get their atomic orbitals back.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when 2 waves travel through each other. Here's a moment when 2 highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the 2 lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the 2 waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
Interference. Let me see if I can explain. When you're dealing with an atom, and this was part of Schrodinger's reasoning when he developed his wave equations for atoms. If you have a certain distance away from a nucleus, and your electron is, say, out here, the electron now is viewed not as a particle, but as a wave. And its ideal position out here is where the wave of the electron is such, if I do this right, is at this distance right there. and forms, and when you come back to this point, it's exactly where it started. Right? That's like the standing wave. A standing wave electron will sit here. And if you give it more energy, then it's got to move out to another level, but it has to move at a certain distance with that circumference to give you the exact wave that'll fit that distance. Now, when you put two of these waves together, when you put two of those waves together, they tend to interact with one another. They interfere. Now, if they support each other, right, with constructive interference, you get the extra highs and the extra lows, then you get, for our molecular orbital model, you get the bonding orbitals. And if they are destructive interference, you get the anti-bonding orbitals. That was the whole point of that video, was to introduce the concept of constructive and destructive interference as it relates to the molecular orbital model. These two overlapping waves are said to be superposed on one another. And they interfere when they do that. Right? We combine their amplitudes. Now we use that, right? We used to use it when radios were invented. Interference was an integral part of sending out that radio wave that you could pick up with your AM radio first and then with the FM, and decode it with your receiver into some, either the spoken word or music or whatever the case may be. What they did was they had a carrier wave. And if you see on the dial on your radio, you see for the AM, it's in kilohertz is the frequency. And for the FM radio, it's megahertz. That's the carrier wave. And what they would do was superimpose the signal on that wave and broadcast that out. And then at the other end, you would just destructively interfere with the carrier wave, and it would release information in the information wave that was superimposed on it. So we've been using this, and we still do that in our internet communication. In fact, we do it not just a single wave, we use multiple compound waves. All right. We call that, we produce a complex pattern. And for the use of our communication systems now, we call it multiplexing. I remember, you probably don't remember this, when we still had vinyl audio recordings, vinyl records, you could get a signal coming out of one speaker and a signal coming out of the other speaker, right? So stereo. And then they came up with quadraphonic, where you could get signals coming out of these two and those two to give you a better surround sound. Well, they did it by multiplexing. And if you took a microscopic look at the groove, instead of just, waves like that, it would be orders of magnitude more information in the jiggles. But that's as far as they could go with a moving needle in a magnetic field, right? You needed digital information to go even further than that. But you could multiplex, you could superpose on the superposed wave. So it'd get really complex. Okay, so let's look at this in terms of molecular orbitals. Right? Like I said, if you can form, gotta go. Okay. Oh yeah. Yeah, that's why I like to do it in one day. That way it's a single recording. When we form the molecular orbitals from the atomic orbitals, the bonding on the bottom, those bonding orbitals are constructive interference, right? For this particular example where we have two hydrogen atoms with their single 1s orbitals, if we get constructive interference, we produce a bonding orbital. If we get destructive interference, we produce an anti-bonding orbital. And like I said before, the bonding orbitals at lower energy than the parents, or the atomic orbitals, and the anti-bonding is at higher energy. Now they've identified these as molecular orbital 1 and molecular orbital 2. What I prefer is if you have hydrogen here with a 1s with its electron and a 1s from the other hydrogen, then when you form the bonding and the anti-bonding, right, then you're going to get two molecular orbitals, and this is going to be a sigma orbital. Both will be sigma orbitals, but this one's going to be sigma star, and the star means anti-bonding. That's the convention. So this one without a superscript is bonding, and that's anti-bonding. And then, of course, you move these electrons. I'm going to jump ahead a little bit. You move these electrons into the lowest possible. We use the Aufbau principle. Electrons go into the lowest possible energy place until it's filled, and then they move to the next level. So you start at the bottom. You got two electrons. They both go into bonding orbital. And there's no anti-bonding with dihydrogen. That's what this would be here. All right. Well, that's what we're looking at there. And as an energy diagram. Notice that the bonding molecular orbital, and this is mathematical calculation, probabilities, puts the most likely location, three-dimensional location for electrons is between the atoms. So the bonding orbitals are going to put their density between the atoms somehow. It may be slightly off axis if they're pi's, but they're going to be between the atoms. And for anti-bonding orbitals, the density is going to be on the opposite side with a node in between. Okay. The nice thing about the calculations that come out of this molecular orbital model is that they do tell us the energies of the bonds. So when we label them, when we say the molecular orbital is sigma, that means the density is on axis between the atoms. If we have to introduce pi, bonding and anti-bonding orbitals, they are off axis. And I think we've got some pictures here coming up. Right, the sigmas are on axis and the pi's would be off axis. We can still only put two electrons in each orbital. And the number of orbitals are conserved. Right? For example, if we have F2 with 18 electrons, then there's the shorthand model. Remember we had shorthand for electronic configurations? You can also have shorthands for molecular orbitals. And for this one, of course, the molecular orbital is going to be a sigma formed from the 1s atomic orbitals and a sigma star formed from the 1s. But this one is going to have both of the electrons in it, right? So you wouldn't even write that one. It would just be, this would be the molecular orbital signature for H2. And we put them in order left to right, from low energy to high energy. That'll make more sense once we actually draw a more complex energy diagram. And, well, I'll leave that statement, that last statement, until we actually get a an energy diagram we can work with. One thing we can do is we can say something about the bond strength without actually calculating the bond strength. We can say something about the bond strength in terms of this new calculation called bond order. Bond order. It's a very simple calculation. Once you get the electronic structure, the molecular orbital structure of your molecule, then all you have to do is count up the number of bonding electrons, right? Number of bonding minus the number of anti-bonding divided by 2. And that's equal to the bond order. So in this case, we've got 2 bonding minus no anti-bonding divided by 2 is equal to 1. So the bond order is equal to 1. Now there's a rough correspondence between what we know to be a fact here, right? These 2 hydrogen atoms are bound by a single bond, that's sigma. That's a single bond order. The difference is that before we could only say it's either a single bond, a double bond, or a triple bond. But with bond order, we can have fractionals, right? We can have a bond order of 0.5, or we can have a bond order of 2.5. All right, so there's our bond order calculation for dihydrogen. Right, I've already done that one. What would happen if we added an electron? Right there. Where would that other electron go? Well, it could come from either side, it doesn't matter. That electron would have to go in an anti-bonding orbital, wouldn't it? Then if we did the bond order calculation, it would be 2 minus 1 over 2 equals 1/2. So what have we done? If we compare bond orders, the neutral dihydrogen molecule is a bond order of 1, but the charged bond order is 1/2. We have weakened the bond, right? The lower the bond order number, the weaker the bond. So by adding that electron, we have weakened that bond. Okay, we got another video.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have 2 isolated hydrogen atoms. And we know that each isolated hydrogen atom should have 1 electron located in the 1s subshell when in its ground state. And of course, we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when 2 atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those 2 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the 2 hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these 2 nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have 1 more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the 2 nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the two atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these two atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these two different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed two new molecular orbitals from our two atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, one from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding. So 2 helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2 p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. You might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma-pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching.
Okay, I know that was a long video, but I thought it was a good explanation. You mentioned the bond order of dinitrogen was calculated to be 3, which implies a triple bond. Nitrogen gas in the atmosphere, it's where it spends most of its time, is very stable and difficult to break that bond. In fact, it's so inert that years ago, particularly potato chip manufacturers like Lay's, for one, were experimenting with ways to keep the oils in their chips from turning rancid, from oxidizing. So the first thing they tried was using antioxidants added to the material itself, but they had some side effects that were not good for your health. So they impregnated the bags with the antioxidants. And I worked with some of those in my master's thesis. But that still was not ideal. So they hit upon the idea of, well, if oxygen's causing the problem, why don't we just flush out all the oxygen with something that won't react? So that's what they do. Whenever you find a bag of chips now, it's kind of puffy, right? They fill it with nitrogen gas. They flush out all the oxygen, and the oils in the chips don't start to oxidize until you open the bag the first time. So you want to eat them pretty quick so they don't turn, not just soggy, but rancid. And I don't know if you've gotten it, let's see, biology, anatomy and physiology, right? What are the primary nutrients for plants and animals? You need water. Plants need carbon dioxide from the air. And they also need nitrogen to make their proteins and their nucleic acids. Well, plants, green plants, can't get the nitrogen they need from the air. They have to have a symbiotic relationship with microorganisms that have enzyme systems to break that bond and fix nitrogen in a form that can be used, either ammonia or nitrate, usually. That's because the bond is too strong for the enzyme systems that exist in green plants. They can't handle it. Okay, so let's move on. So the examples that were given in that video were homonuclear diatomics. That is, 2 atoms, both the same elements. And you'll notice that when the discussions centered on creating the molecular orbitals, we were only using the top valence electrons. We weren't even using the 2 s's, right? We were focused on the 2 p's or the 3 p's or whatever the case may be. And as far as calculating the bond order goes, you don't need the ones at the lower levels because they're all full anyway. So they're going to cancel each other out. We want the higher level that can tell us something about the bond. So we typically exclude the core electrons, although they are there and they have their molecular orbitals. Right? Don't misunderstand. But we only use the valence electrons in our discussions because that simplifies things. All right, the narrator also emphasized this point. One thing that the valence bond theory, the localized electron model, does not explain is this phenomenon that we see in some compounds called paramagnetism versus diamagnetism. Paramagnetism means that the compound is drawn into a strong magnetic field. Oxygen is like that. Diamagnetism is one where the compound is repelled from the magnetic field. All right, so only the molecular orbital model can explain that, because when you have two electrons in the same orbital like this, one spinning this way and the other one spinning that way, they generate a magnetic field. And if one's going this way and one's going that way, they cancel their magnetic fields out. All right. So they're essentially magnetically neutral. But if you have unpaired electrons, like oxygen does, then that one produces its magnetic field that way and that one there, so they reinforce one another. Unpaired electrons are required for paramagnetism. Let's see, I think I got a picture. Well, we can calculate the paramagnetism. Well, we can measure it actually. So you take your sample and you lower it into a strong magnetic field, and you measure whether it's pulled by the field or repelled by the field using a balance. Now, this is an oversimplified version, but it makes the point. Here's an example where oxygen, liquid oxygen, is poured into a strong magnetic field. Have you ever seen one of these horseshoe magnets? Yeah, they're fun to play with. They're huge, like big, and they bring them together here. So the gap between the north and south pole is very small. And that means the strength of the magnetic field in between them is very large. So when you pour your liquid oxygen into that gap, it stays there. You can see it in the right-hand plate. Until, of course, it evaporates. That's why we use liquid. I mean, if you just poured oxygen gas in there, it might stay there, but you wouldn't be able to see it. So we use a liquid. Oh, Professor Dave's going to talk now.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of two atomic orbitals will always result in two molecular orbitals, one bonding and the other antibonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 anti-bonding electrons, including the sigma 1s star anti-bonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have 2 unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, there's that diagram. And we were focused on this place right here where we go from nitrogen to oxygen. When we looked at oxygen, we had the sigma below the pi, and then the pi star, and then the sigma star. So you had the sigma pi, the sigma and the sigma star at the extremes, and the pi star in the middle. That's the way I look at it. When we go from right to left, difluorine, dineon doesn't make any sense. There's no such thing. But difluorine and dioxygen have no mixing. And then when you get to nitrogen and further left, then you get the switch places with the sigma and the pi. So the pi now is lower energy than the sigma. So that just affects the way you draw your energy diagram. Where you would normally have sigma here and pi here, and then pi star here, and then sigma star here. With mixing, these two flip, and pi is at lower energy than sigma. Excuse me. Here's another diagram that actually gives you more information. It gives you the molecular orbital configuration for each of the homonuclear diatomics. And it also incorporates calculated bond orders, whether it's paramagnetic and diamagnetic. Notice that the paramagnetics have unpaired electrons, right? There are two of them in there. The dioxygen and the diborane. And the others have all paired electrons, so they're diamagnetic. And then you have the observed bond energies. They increase, the diboron, the dicarbon, and the dinitrogen increase from left to right. Then when you get to the oxygen, you get the the anti-bonding electrons come in and the bond order drops and the bond energy also decreases. In fact, oxygen is a stronger bond energy than fluorine, difluorine. And this also has an effect on their bond lengths, but we're not going to spend a lot of time on that one. Okay. There you get SP mixing. Sometimes they say sigma pi mixing rather than SP mixing because SP implies their atomic orbitals are mixing, but they're not actually atomic orbitals that are mixing. They're molecular orbitals. Okay, so we can also discuss this situation in terms of heteronuclear diatomic molecules. And our first example here is carbon and oxygen, right? Carbon monoxide. If we drew carbon monoxide according to this theory, then it would have like that, like that, like that, like that. Okay. But when we put the carbon's orbitals are going to be higher energy. You remember why they're higher energy than oxygen? Look where they are on the periodic table. Carbon's over here, oxygen's over there. As you move to the right, the effective nuclear charge increases. So that draws not just the electrons, but the orbitals. It shrinks the orbitals into a lower energy state. So oxygen's going to have its S's and P's at lower energy than the carbons. So then this takes some fancy calculating and some experience that I don't have. Chemistry majors probably have to spend a whole semester on just this stuff, but I never got that. But just to make the point, it looks like when you combine the two s orbitals, you get an s bonding and an s antibonding there, and then between the two, you get another sigma. Notice that when you have the two p's right here, 2p here, 2p here, when you combine two of those, the first one you get at this lower orbit in energy are sigmas from the two p's. Then you got two here and two here left over, and they go into these pi's from the two p's and pi's from the two p's. Right, and then I think the next one is sigma star. All right, so instead of a pi star, we get a sigma star. That implies sp mixing. All right, so let's see, carbon and oxygen. Well, if we had dioxygen, there would be no mixing. If we had dicarbon, there would be mixing. So there's no way to tell. You have to be told, or you have to assume that since carbon is further to the left, it's to the left of nitrogen, then the carbon has an influence on the mixing, where instead of getting the pi stars here, you get the sigma star, and then you get the pi stars. Made from the two p's. Okay. And then we have, let's see, I left one out, didn't I? Yeah, I left one out. There's another one up here. Sigma star from the two p's. Two p's. Now I'll see if that's right. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Oh, I left out the two s's. Right, so the two s's. Two s's go right there. Okay, so that's an example of a heteronuclear diatomic, carbon monoxide. And they filled in the electrons for the second level. We left out the 1s level, it's down below. And what we end up with, if we calculated the bond order of this one, the bond order, we just look at our diagram and count up the bonding electrons. So I see, let's see, there are 4 in the pies, and then there's a sigma and another sigma. So it's 2, 4, 6, 8. So we got 8 bonding. How many anti-bonding? Just 2. Divided by 2. So 6 divided by 2 is 3. That gives us bond order 3, which corresponds to our triple bond. How about heteronuclear diatomics with HF? Hydrogen only has a 1s orbital, right? At very low energy. And then the HF would have to combine its 2 p's because those are the valence electrons. All right, so this is the diagram that you would see. Well, since the nuclear charge on hydrogen is just 1 proton, actually the 1s is higher than the 2p for fluorine, because fluorine is way to the right. It has 9 protons in its nucleus. So that's counterintuitive, right? You would expect the 1s to be lower energy than the 2p. But that's only within an atom. In this case, the 1s is higher. So when you combine the two, you can only have 1s from the hydrogen and whatever the highest level energy from the fluorine to combine. Now, of course, the others do combine. Actually, I'm not sure how they handle that, right? Because hydrogen only has the 1s to combine. So I assume there's a workaround there. Just don't know what it is. Okay. The prediction is that it should be stable because both electrons are in bonding orbitals. We should have a bond order of 1. But we already know that the electronegativity of fluorine is much, much higher than hydrogen. So even though we have a sigma bond between them, the sigma bond is going to be, the electron cloud is going to be more concentrated toward the fluorine. All right, so that will weaken the bond a little bit. Okay. I'd already said that. The pair is not shared equally. And we should expect a polar bond. Now, this idea of delocalization, what we get in delocalization, actually what we're going to do now is combine these two theories to try to understand the stability of certain types of molecules. Those that have pi bonding in them tend to stabilize the molecule. And especially if you can get a pi bonding in a circular fashion. And the perfect example there is benzene. Right? If we drew the dot structure for benzene, right, it would be a ring. You'd have a carbon at each one of these places right here. And then there's a hydrogen attached to each one. Right, I'm drawing it out. In organic chemistry, we don't draw hydrogens, we don't draw carbons. Anywhere 2 lines meet in organic, there's a carbon. It's just to save space. But we need an octet. So we got a double bond here, a double bond here, and a double bond there. And that uses up all of our valence electrons. But this can resonate between this structure, and if we move the double over here, the double here, and the double here, you get another possibility. But that doesn't explain the stability of the molecule, because we know all of these bonds are exactly the same length and exactly the same strength. So we have to delocalize those pi electrons. Right? If we get an sp2 hybridization, which would be trigonal planar, and this whole molecule is planar, then we have the 1 pi orbital, unused p orbital for each carbon that can overlap. And what they do is they overlap in a donut and delocalize the electron density both above and below the ring. This is known as a conjugated aromatic system. Now, there's some rules that tell you whether a molecule is aromatic and not aromatic. And aromatic means very, very stable situation. We can also see this with not just ring structures, but we can see it with this representation of the nitrate molecule, right? We can draw three separate structures, Lewis structures for the nitrate, and in the past we had to resonate them because they were all equal. We couldn't choose. But its pi bonding system can also be delocalized, and that stabilizes the molecule. I think this is the last slide. What we want with our theories is that our theories agree with reality. In other words, when we make measurements of a system of any kind, atomic, molecular, and the theory predicts those values, whatever the case may be, then we say our theory is in agreement with the experimental. And this is one measurement technique. This photoelectron spectroscopy is one method that agrees with the theory. So what we're doing is we're trying to determine the relative energies of electrons in atoms and molecules. So what we do is we fire high energy photons at the sample, and the electrons that are in that molecule absorbs some of that energy, and the energy required to free the electrons from the atom is a certain amount, and any extra gives them kinetic energy. Okay, you've heard of the photoelectric effect. When you shine ultraviolet light on a metal, it'll eject electrons. Right, so there's a certain amount of energy that's required to eject an electron. It's called the work function, and all that energy is used to move that electron from the highest orbital to infinity. But once it gets there, if there's any energy left over, it's translated into kinetic energy, and that's what we're measuring here in terms of voltage. So once we find out what that kinetic energy is, then we can compare it with what we expect from the model, and it agrees perfectly. The measurements agree with the calculated values of energies for the electrons based upon the molecular orbital model. All right, so that's probably enough. At least you were kind enough not to fall asleep.